Hello, chemistry students. Today we will be performing our extraction experiment. The extraction technique allows chemists to isolate and purify organic substances by mixing a solution with a second solvent that is immiscible with the first. The organic solute is extracted into the second solvent because it is more soluble in that solvent. In this experiment, we will introduce the microscale technique for performing extractions. Let's get started. In part A of this experiment, we're going to be performing an extraction of caffeine using methylene chloride. And we first need to add approximately 70 milligrams of caffeine to a screw cap centrifuge tube. The mass of caffeine that we will be using is 0.0719 grams. I've added our caffeine to the centrifuge tube, so we're now going to add 4.0 milliliters of deionized water to our centrifuge tube. And we'll need to shake our tube for several minutes until the caffeine has completely dissolved. All of the caffeine has dissolved in our water, so we'll now perform our first extraction by adding 2 milliliters of methylene chloride to our centrifuge tube and mixing thoroughly for about 1 minute. You should also vent your centrifuge tube to release any pressure when performing extractions. Once mixed thoroughly, place your centrifuge tube back in the rack and allow the layers to separate completely. Once the layers have completely separated, we'll transfer the bottom organic layer to a clean test tube using a Pasteur pipette. We'll now repeat this extraction 2 more times using 2 milliliters of fresh methylene chloride each time. We've collected our 3 2-milliliter extractions of methylene chloride in a test tube. And you can see now that we just have one layer, which is our organic layer of methylene chloride in our test tube. And we're now going to completely dry our organic layer using anhydrous sodium sulfate. And we'll add anhydrous sodium sulfate to our organic layer until the sodium sulfate is free-flowing and no longer clumps. This will indicate that our organic layer has been completely dried. Now you can see that our anhydrous sodium sulfate is free-flowing in our test tube and is not clumping. This indicates that our organic layer is completely dry. We'll now set our test tube in the rack and stopper it and allow it to continue drying for a period of about 10 to 15 minutes. While our methylene chloride solution continues to dry, we need to pre-weigh a 10 milliliter Erlenmeyer flask. The mass of our 10 milliliter Erlenmeyer flask is 14.8452 grams. We will now make a filter tip pipette, which can be used to remove a small amount of solid from a volume of liquid. Now, the filter tip pipette is similar to a filtering pipette, except we will be using a much smaller portion of cotton, and we'll place this cotton in the open end of our Pasteur pipette. We'll then use a very thin copper wire to push the cotton all the way down to the end of our pipette tip. And this is one way to make a filter tip pipette. We'll next use our filter tip pipette to transfer the dried methylene chloride to our pre-weighed 10 milliliter Erlenmeyer flask while leaving the sodium sulfate. We then need to evaporate off the methylene chloride in our 10 milliliter Erlenmeyer flask in a hot water bath. We're now evaporating the methylene chloride from our 10 milliliter Erlenmeyer flask in a hot water bath, and we're aiding the evaporation using a stream of air. We've evaporated all of the methylene chloride from our 10 ml Erlenmeyer flask, so at this point we will weigh the flask to determine the amount of caffeine that was in our methylene chloride. The mass of our 10 milliliter Erlenmeyer flask and the caffeine is 14.9084 grams. You can now determine the amount of caffeine that was in the methylene chloride. This concludes part A of this experiment. In part B of this experiment, we're going to look at the distribution of a solute between two immiscible solvents. In particular, we're going to be looking at benzoic acid, succinic acid, and sodium benzoate. And we're going to investigate how these three organic solids distribute themselves between water and methylene chloride. And we're going to start with benzoic acid, and we need to transfer 50 milligrams of benzoic acid into a 5 milliliter conical vial. The mass of benzoic acid is 0.0516 grams. I've added our approximately 50 milligrams of benzoic acid to our conical vial. We'll now add 2 milliliters of methylene chloride and 2 milliliters of deionized water to our conical vial, and then we'll cap and shake to mix for approximately 1 minute or until all the solid has dissolved. Now that we've thoroughly mixed our benzoic acid with the 2 milliliters of water and 2 milliliters of methylene chloride, we're going to remove the bottom organic layer and transfer to a clean test tube, and then we're going to dry that organic layer with anhydrous sodium sulfate. While we allow our organic layer to continue to dry, we'll pre-weigh a test tube. The mass of our test tube is 7.9774 grams. We'll now transfer our dried methylene chloride solution to our pre-weighed test tube using a filter tip pipette. This will ensure that we leave the drying agent behind. We'll next evaporate off the methylene chloride from our test tube by placing the test tube in a hot water bath and directing a stream of air at the surface of our solvent. We've evaporated off all of the methylene chloride from our test tube, so we'll now determine the mass of our pre-weighed test tube and the solid benzoic acid remaining inside the test tube. This will allow us to determine the amount of benzoic acid that was in our methylene chloride layer. The mass of our pre-weighed test tube and our benzoic acid is 8.0170 grams. We'll now repeat the procedure using succinic acid instead of benzoic acid, and we first need to transfer approximately 50 milligrams of succinic acid to a 5 milliliter conical vial. The mass of succinic acid is 0.0529 grams. We'll now add 2 milliliters of methylene chloride and 2 milliliters of deionized water to our 5 ml conical vial with our succinic acid. We'll now transfer the bottom organic layer of methylene chloride to a new clean test tube and dry the organic layer with anhydrous sodium sulfate. As we wait for the organic layer to dry, we need to pre-weigh a test tube. The mass for our pre-weighed test tube is 8.0035 grams. We'll now transfer our dried organic methylene chloride layer to a new test tube using a filter tip pipette. We've evaporated all of the methylene chloride from our test tube, so we'll now weigh the test tube to determine the amount of succinic acid that was in our methylene chloride layer. The mass of our test tube and succinic acid is 8.0052 grams. We'll now repeat this procedure one last time using sodium benzoate. We first need to transfer approximately 50 milligrams of sodium benzoate to a 5 milliliter conical vial. The mass of sodium benzoate is 0.0491 grams. We've transferred our approximately 50 milligrams of sodium benzoate to our 5 ml conical vial. We'll now add 2 milliliters of methylene chloride and 2 milliliters of deionized water to our conical vial and shake to mix for about a minute until all of the sodium benzoate has dissolved. We'll now transfer the bottom organic layer of methylene chloride to a clean test tube and dry the organic layer with anhydrous sodium sulfate. While our organic layer dries, we need to pre-weigh a clean test tube. The mass for our pre-weighed test tube is 5.2857 grams. We'll now transfer our dried organic layer of methylene chloride to our pre-weighed test tube using a filter tip pipette. We've evaporated off all of the methylene chloride from our pre-weighed test tube, so we'll now weigh our pre-weighed test tube to determine the mass of sodium benzoate that was in our methylene chloride layer. The mass of our pre-weighed test tube and sodium benzoate is 5.2873 grams. You can now determine the amount of each of our 3 organic compounds in methylene chloride and water, and you can also determine their distribution coefficients. This concludes Part B of this experiment. In Part C of this experiment, we will learn how to determine which is the organic layer of 2 immiscible solvents. We'll do this by adding several drops of water to the top layer. If the water adds to the volume of the top layer, then the top layer is aqueous. If the water balls up and forms a third layer, then the top layer was organic. Let's get started. The first pair of liquids contains water and n-butyl chloride. We'll now add several drops of water to our test tube containing water and n-butyl chloride. Note which layer has gained volume when adding the water. Our second test tube contains water and n-butyl bromide. We'll now add several drops of water to our test tube containing water and n-butyl bromide. Our third test tube contains n-butyl bromide and saturated aqueous sodium bromide. We'll now add several drops of water to our saturated aqueous sodium bromide and n-butyl bromide. You can now determine if the organic layer was the top or bottom layer in each of our 3 test tubes. This concludes part C of this experiment. For part D of this experiment, we will use extraction to isolate a neutral compound from a mixture containing an acid impurity. We will then identify the isolated neutral compound by taking its melting point. Our mixture of acid impurity and neutral compound is unknown number 2. And we'll start by transferring approximately 150 milligrams of unknown number 2 to a centrifuge tube. The mass of unknown number 2 that we will be using is 0.1521 grams. I've transferred our approximately 150 milligrams of the unknown number 2 mixture to our centrifuge tube, and we're now going to add 4 milliliters of diethyl ether to our tube, and we'll shake until all of the solid has completely dissolved. Now that our solid has completely dissolved in the ether, we're going to extract the acid impurity by performing 2 extractions using 2 milliliters of 1.0 molar sodium hydroxide. And we'll collect each extraction in a separate test tube for the first extraction and the second extraction. So we're going to add 2 milliliters of 1.0 molar sodium hydroxide to our test tube. We'll shake for 30 seconds and then allow the layers to separate. Now that the layers have separated, we're going to remove the bottom aqueous layer using a Pasteur pipette and transfer to a test tube for the first sodium hydroxide extraction. We'll next add a fresh 2 milliliters of 1.0 molar sodium hydroxide to our test tube with the ether to perform the second extraction. We'll now remove the bottom aqueous layer using a Pasteur pipette and transfer to a separate test tube for the second sodium hydroxide extraction. We are next going to add 6 molar hydrochloric acid dropwise with stirring to our test tubes containing the first sodium hydroxide extract and the second sodium hydroxide extract. And we'll test that the solution has become acidic with pH paper. You can see that we've made our first sodium hydroxide extract acidic with the addition of the 6 molar hydrochloric acid. And this is what our extract now looks like. We'll now add 6 molar hydrochloric acid dropwise to our second sodium hydroxide extract. And we'll test the pH with pH paper. And you can see that we've now made our second sodium hydroxide extract acidic with the addition of the 6 molar hydrochloric acid. And this is what our second sodium hydroxide extract now looks like. We have our first and second sodium hydroxide extracts after the addition of the 6 molar hydrochloric acid. And this is our first sodium hydroxide extract and our second sodium hydroxide extract after the addition of the 6 molar hydrochloric acid. You can now draw some conclusions regarding the removal of the acid impurity from our mixture using the sodium hydroxide extracts. We next need to dry our ether layer, and we're going to start with the addition of 2 milliliters of saturated sodium chloride solution, and we'll shake for 30 seconds. Now that our layers have separated, we're going to remove and discard the bottom aqueous layer into a beaker. We're then going to transfer the ether layer without any water into a clean test tube, and we're going to dry the ether layer with anhydrous sodium sulfate. While we allow our ether layer to dry over the anhydrous sodium sulfate, we'll pre-weigh a clean, dry test tube. The mass of our pre-weighed test tube is 8.0370 grams. We'll next transfer our dried ether layer to our pre-weighed test tube using a filter tip pipette. We'll next evaporate the ether from our pre-weighed test tube by placing the test tube in a hot water bath and directing a stream of air into the test tube. The mass of our pre-weighed test tube and our unknown solid is 8.1170 grams. We now need to take the melting point of our unknown solid and identify it from the following list. We will now determine the melting point of the unknown neutral compound in unknown number 2. This concludes part D of this experiment. Okay, students, we've now learned how to perform a microscale extraction. We've investigated how organic solids distribute themselves between aqueous and organic solvents, and we've learned how to isolate and identify a neutral compound from a mixture containing an acid impurity. This concludes our extraction experiment. Thank you for joining me for this laboratory.